Okay, so let's look at a very simple animation of taking the Fourier transform of a function. So are you ready? So let's start and let's try to understand how we are taking the Fourier transform of a very simple function. So we start with the Fourier transform. This is the definition of the Fourier transform of a function. This is the convention without coefficients before the formula, but this is the Fourier transform of the function f of t. And f of t comes here, multiplying by the exponential and taking the integral. This is the Fourier transform of the function. The Fourier transform transfers the function from the time domain to the frequency domain. So what we are going now to do is to take the Fourier transform of this function. This is the sinus 6 pi t. This function have a frequency of 3 Hz. So what we expect is that the Fourier transform of this function will give us a solution of 3 Hz, namely the frequency will be 3. It's sinus, so the magnitude will be complex number, but the frequency should be 3. So we continue. This is the function, this is the Fourier transform. Now we plug in this function in the Fourier transform. And here is the function multiplying the exponential, taking the integral. This is the Fourier transform of our function. And we continue. We continue by noting that this is the Euler formula for sinus e to exponential of 6 pi minus e exponential this divided by 2i. And we continue. We continue by plugging in the Euler formula instead of the sinus in the formula of Fourier. So we get this. Now, this is the Fourier transform we get to until now. And now what we are going to do is to open the parentheses and insert the exponential inside. Let's look how it happens. So here it is. We plugged in, we entered the exponential inside, and now it is beside this one and beside this one, and the constant we took out. Now we can use the rule of exponential multiplication and take this one and combine them to one exponential with different to the power different power. So let's look how it happens. So yeah, you can see how we change this according to the rules of exponential multiplications. Here we did the same and we continue to calculate it. Now what we are going to see is the use of Dirac's function. Dirac's function. What the Dirac function says is that this integral can be identical or equals to the Dirac's function with the value of this, namely 6 pi minus omega equals here what in the Dirac function. Okay, so this integral is being replaced by this, and this integral is being replaced by this. So the Dirac function, what you should remember is it is 0 everywhere except it 0. So we are looking at the Fourier transform, which is this, is 0 everywhere except for when the value here is 0 or the value here is 0. Therefore, we got that omega has two solutions. I'm not sure it shows it here, but this is the Fourier transform of the function. Now the solutions are when the Fourier transform is not 0. So it happens when omega equals 6 pi or omega equals minus 6 pi. Now remember that omega equals 2 pi f. Therefore, if omega equals 6 pi, and 2 pi f, so f is 3 hertz. And here you get that f is minus 3 hertz. Again, omega equals 2 pi f, and it should be 0 here, so 2 pi f equals minus 6 pi, so f, this is the frequency, is minus 3 hertz. Now this is the amplitude of the magnitude of this frequency. It's a complex number, the coefficients, because we deal with sinuses. If we were dealing with cosinus, it would be real number. If we would have dealt with sinus and cosinus, so it would be real and imaginary number. So yeah, this is the Fourier transform. Now let's look at it from the start to the end without interruption, just a little bit of talking. So Fourier transform, this is the formula, the definition of Fourier transform. We took the form of ft equals sinus 2 pi t. We plugged it in the Fourier transform, as you can see here. Then we used the identity, the Euler identity, the Euler formula for sinuses. We plugged it in the Fourier transform and got this formula. Now we open the parentheses and insert the exponential inside. We use the rules of exponential to get what we are getting now. We use the Dirac function, Dirac identity, with exponential to get this. Therefore, we get that the Fourier transform of our function is this. And from this one, we can conclude what are the frequencies of our signal, our function, sinus 6 pi t. This is the function in the frequency domain. So this is it. This was about the Fourier transform. Thank you very much. We didn't talk about the inverse Fourier transform, it just was animation of the Fourier transform. If there are any corrections, please correct me. Thank you very much. This was about the Fourier transform, and this is it.